Alright, today I'm going to teach you a few different extensions of graphing. The first one is how to graph quadratic inequalities. So this is similar to when you're graphing a linear equality. The only difference is we're going to have parabolas instead of lines. So first thing we're going to do is we're going to graph the boundary parabola. And you're going to keep in mind that if the equation is just less than or greater than, you're going to use a dashed line. And if it's or equal to, then you're going to use a solid line. Okay, step 2 is you're going to pick a test point not on the parabola. And then step 3, you're going to shade where the inequality is true. Which is either going to be inside the parabola or on the outside. Okay, so let's go ahead and try an example. The first thing you're going to start with is just graphing the parabola. You can pretend that this is an equal sign. What I'm noticing about this first equation, I could just graph right away from standard form, finding the vertex, but I'm noticing that this one is also factorable to x minus 2, x minus 1. So that's telling me that my x-intercepts are at 2 and 1, and that's going to help me find my vertex right in between those at 1.5, and when I plug that in, I get negative 0.25. Now, of course, you could always use your graphing calculator for this too, and that might help you find the vertex quicker. Since this is a greater than problem, if you want to, you can do an XY chart as well. So I could figure out a few more points on my parabola to graph. I already know I've got 1.5, 0.25, 1, 0, and 2, 0, but if I plug in 3, I get 2, and if I plug in 0, I'm also going to get 2. So those are two more easy points to plot. Okay, now since this is greater than, I'm going to make this parabola a dashed line. Okay, so I've got step 1 done. Just graph the boundary parabola. That's what we've worked on all chapter. The next step is to pick a test point not on the parabola. So I think a good test point would be 0, 0 because that's clearly on the outside of the parabola. So if I plug in 0 for x and 0 for y, I get 0 is greater than 2. This is where you're thinking about that inequality sign again. Is it true that 0 is greater than 2? No. So I don't want to shade where 0, 0 is. I want to shade on the opposite area, which would be on the inside of the parabola. That's really all there is to it. There's a big key in graphing the parabola, then you're just picking a test point and shading. Let's try number 2. Number 2, again, I think I'll just use my calculator to figure out that the vertex is at negative 3, 2. I could go through x is negative times negative 6 over 2 times negative 1. Positive 6 over negative 2 gives me negative 3. And when I plug that in for x, I get 2 for y. I'll also do a little XY chart, since this was standard form. Negative 3, 2 was my vertex, so I'll plug in negative 4, negative 5, negative 2, negative 1. And so I'm going to get 1 and negative 2 for my other points to plot. Here's my vertex. This is a parabola that does open down. Since this one's an or equal to sign, I'm going to go ahead and make it a solid parabola. Okay, again, I think 0, 0 would be a decent test point because it's clearly on the outside of the parabola. If 0, 0 was on my parabola, I'd want to choose something else. But in this case, 0 will work. So I get 0 is greater than or equal to negative 7, which this time is true. So this time I want to shade where the 0, 0 is, which is on the outside of the parabola. So that's graphing inequalities. Again, the big thing was just to graph the parabola, pick a test point, and shade. The next type of extension that we want to look at is what happens if I give you a table of values. If I gave you a table of values for a quadratic equation, could you figure out where the x-intercepts were and where the vertex is? So remember, for an x-intercept, that means it's hitting the x-axis somewhere. And what you're going to have is a change in the y-coordinate from negative to positive or from positive to negative. For the vertex, you're also going to look for the y-coordinate, and you're going to look for it to reach a max or a min. Alright, so let me show you some examples. It says use the table below to answer the following questions. Remember, the first thing I'm looking for is a change in sign for the y-coordinate. That's what's going to give me the root, or in other words, the x-intercepts. If I actually look closely at this table, I know what the roots are because roots happen when y is 0. So the roots for this problem are very clear. They're at 2, 0, and 6, 0. Now I know that the vertex is going to be somewhere in between there, so I'm looking for where does the graph hit its highest point or its lowest point. Since it hits 12 twice, it seems like on the outsides of the table, the graph is getting bigger. But at this very middle point, it hits a low of negative 4. So that's actually where my vertex is going to be, 4, negative 4. And then the y-intercept, this is just an extra point. This is when x is 0. So if I look at x being 0, I can see that the y value is 12. Now that was a pretty easy one. So finding the roots, you're looking for where is y 0. Or where does it have a sign change if it's not as clear as this one. For the vertex, you're looking for a max or a min. And for the y-intercept, you're looking for where is, or what is the value when x is 0. Alright, let's try a little bit trickier example. So first thing is approximate the x values where the zeros will occur. Now this time when we look at our table, there are no places on the y chart where we have 0. But we do have a couple of places where there's a sign change, and the sign changes from negative to positive or from positive to negative. So your zeros are going to be somewhere in between there. I'm not going to be super picky about this answer, but because it's from negative 2 to negative 3, it's going to happen somewhere in between these two x values. So my zeros are going to occur at negative 2.5. That would be a good thing to put in between. And somewhere between 0 and 1, we'll say 0.5. If you wanted to say 0.6, you wouldn't necessarily be wrong, but I'll just let you choose somewhere in between those 2 points for now. For approximating where the vertex would be, I'm looking again for the max or the min. This time I'm noticing that at my extremes, this is getting more and more negative. So I'm looking for a point where it reaches its highest point, which happens somewhere around the negative 1,9 mark. So I'm going to go ahead and let you say negative 1,9 is the vertex. And then the y-intercept, again, happens when x is 0. This one needs to be exact. It's from our chart, 0, 7. The rest of our notes for today are actually pretty much a review from transformations. But it's, again, might be phrased a different way than we've talked about. So let's go over it. The first part is, tell what transformations have been done to a graph. The big thing here is, again, if I give you a picture of a parabola, you want to identify where is the vertex. So for this one, it looks like the vertex is at 3, 3. And once I have that, everything else is usually pretty easy to find. axis of symmetry is going to be x equals 3. Domain is always negative infinity to positive infinity. The range goes from negative infinity all the way up to 3. Okay, and then I can also figure out my x-intercepts are somewhere in between 1 and 2. Now it looks to me like it's a little bit closer to 1, so I'm going to go with 1.2 comma 0, and then somewhere in between 4 and 5, a little bit closer to 5, so I'll go with 4.8 comma 0. If you wanted to say 4.7, you wouldn't be wrong, since we don't know exactly where that is. Alright, the equation for the graph, we've done this lots of times. If I have the vertex, I just want to plug it in opposite, so x minus 3 squared plus 3. And then the transformations that have been done to the graph, this is what we've also been talking about in this chapter. I've got the graph is moved right 3, up 3, and flipped over the x-axis. It looks like it's pretty normal since normal width, since we're going down 1 over 1, and then from there down 3 over 1. So I don't need any extra stretching or widening happening here.